Yeah, thank you. Thank you so much. Thank you all for having me. I'm really excited to be here today at UCF to share with you my work and my vision in cooperative multi-agent RL. My I do research in autonomous system where there are multiple intelligent decision-making agents cooperating together to achieve a common goal. These agents can be physical agents, for example, doing drone delivery or managing a power grid, or they can be just virtual agents doing automated design and playing multiplayer video games. I came from the AI perspective, where the problem is often framed between the agent and its external environment. At each time step, the agent will use its control policy to select its decision, which we call an action, and that action will affect the state of the environment. And the environment will present the agent with observation and a scalar feedback, which we call reward, to measure how good the agent is doing at the current time step. And based on those signals, the agent will modify its internal state and then select the next action. So this loop will iterate over time, and the agent goal basically is to maximize its reward signal, which is measuring how well it is doing over time. And the techniques, the methods that are for the agent to modify its internal state and to select its control policy is called planning and reinforcement learning from the AI community. But there are many other terms that doing the different thing from different companies. And this is the core framework that has driven many recent advances in AI, including in the game of Go, in learning-based robotic locomotions, and even in ChatGPT's training. So this kind of framework is kind of the core driver there. In this talk, we are mostly interested in a setting where there are not a single agent, but a team of agents forming this team to achieve a common goal. So the picture will be modified as this. So every agent will receive its observation OI, and based on which they will select their actions individually or respectively. And those actions will collectively affect the state of the environment. And this loop will go on and on. The caveat is that the reward is still shared between multiple agents, indicating that they are a team. There's no different interest in terms of their goal. So and this problem is particularly challenging in two aspects. One is for each individual agent, it still needs to deal with its high-dimensional state and action spaces. It has to deal with long decision horizon to maximize, the reward over a long period of time, which makes this problem often data and compute hungry. And the other aspect is about this multi-agency. So usually the agents in the team are often uncertain about others' intent. For example, in this two-card example, the green card is not sure whether the blue card is going, straight or making a turn, right? So, and in general, each agent only has a myopic and imperfect information of the global picture. And fundamentally, the complexity of the problem often scales exponentially with the number of agents. So which, this challenge makes this problem often communication hungry, because agents need to communicate with each other to better understand each other, to better understand the global picture. Okay, so therefore, my research is aiming to achieve data, compute, and communication efficient cooperative planning and R. And if you plot this goal as a diagram, we'll plot those resources that we are using along this horizontal axis, and the team reward on the y-axis. So we want to push the performance curve to the top left. My approach takes the inspiration from human society and nature to study structures that are in this teams. For example, if you view traffic management as a multi-agent problem, because you can place different traffic controllers like traffic signal at different places, then it's every traffic signal can be viewed as its agent, and they are collectively trying to manage the road. And to solve this problem, we humans build RoadNet, we build traffic signal, we will use turn signals to indicate cars' intent. Another example in nature is that, for example, these ants in a colony, they are organizing themselves with a hierarchy of rows, where there are multiple worker ants and a few queen ants perhaps doing different jobs. And in most engineering applications, typically mechanical engineering, those agents are often operating in a physical world, which is often in R3 or Euclidean spaces, where there are multiple geometrical properties that is structuring the team. So these are three different examples of three different structures that are, in those teams, which can make cooperation a little bit more, easier, right? So, and my goal is my approach is to discover and formulate or engineer or and exploit those structures in the multi-agent teams. In doing so, I look for provable guarantees and also deep learning-based solutions for practical, issues. When I say practical, I'm the practical in the sense that I have some successful stories still in the simulators, but I look for opportunity to extend this success to real, deployable applications. So this part has been quite effective for me. This slide summarizes my past and current research in this different topics, starting all the way from my PhD study. I earned my PhD in the year of 2020. So, right. And next, I will highlight the three works and one from each category. So the first work is about structured communication over context-aware base net. And to motivate the problem, we will use this two robot vacuum example. Suppose there are two robot vacuums cleaning the house, and without proper coordination, they might simultaneously clean the same spot, which is undesirable because it's inefficient and can even cause collision. What we really want them to do is to first explore different spaces so they can discover different dirty spots, and then they clean different spots individually and respectively without too much interference with each other. But how do we do that, right? So one approach is by what I call action communication. So in this example, the blue robot can say at the beginning, I will check around so I can sort of figure out where the dirty spots are. And after getting this message, both by the red agents, both agents start exploring the spaces and discovering different dirty spots. And that at that point, the blue robot will say, I will go left to sort of communicate its intent. And the red robot, after getting this message, will go to a different spots. Right. So using the language of probability, we say the blue robot action A1 is coming from its policy pi1, and A2, the red agent's coming from its red policy pi2. Without any action level communication, they have to select their action independently given the current state. But with this, action communication, the red agent sort of can select its action A2 based on the action of A1. The blue agent communicates, right? And the probability tells us that this can model arbitrary joint distribution between the two actions. So it's slightly more expressive than the individual no communication case. So generalizing this idea to an arbitrary of n agents, we can say if we don't have any action level communication between each other, they have to select their action independently given the current state. But if you want to model arbitrary joint action distribution between them, which is desirable for a cooperation, so you sort of have to do this full dependence case where agent I's action has to be selected based on all the previous I minus one agents. So this diagram, if you're doing a base network, it has to be sort of connected in a dense manner. So the left part case is called product policy because we are doing a product of n policies. Some people call it fully decentralized policy. Obviously, the good thing is that the action space scales only linearly with the number of agents. There is no issue of communication, but the downside is the cooperation might be difficult. On the right-hand side, we have a full dependence case where because you can model arbitrary joint distribution between agents, it's effectively a single agent thing, and you can have similar kinds of performance guarantee as you will get in a single agent setting, which means that cooperation will be easier. But the obvious issue is that the action space scales exponentially with the number of agents, because agent I has to wait for the previous n-1 agents to sort of decide on its own action. There's obviously a delay when they are making a choice. Okay. So which means that neither of the cases is fully satisfactory to us. Okay. So but the natural question is, can we combine the best of both worlds? The answer that we provided in this work is very straightforward, right? We just put these two cases as the two ends, the two extreme cases on this spectrum. And what we really want is something in the middle. We basically want to remove this redundant communication, this redundant dependency between these agents, and keep those communications or actions dependency that are really important to us. So in this way, we want to model arbitrary independence or dependence between those agents' action selection. And we can sort of model this with the BaseNet, right? So that's a core idea of this work. But the natural question is, how can we decide which edges to remove and which edges to keep? So in this, for example, 3 vacuum example, if those agents, those robots, they have already found their different dirty spots, then they don't have to communicate with each other too much. And we will put them on the left end. It's a full independence case. On the other side, if they are just beginning, they don't know what to do yet, they even don't know where they are going yet, they have to sort of perform some level of extensive communication with each other to figure it out. So we put them on the right end. And the general case is somewhere in the middle, where maybe some agents don't need to communicate with others, some agents has to communicate with each other. So that's the general case. The model of the story is that we really want that dependency to be in a context-aware manner. So depending on where the agents are, what they are doing, and to decide what the communication is. And you can sort of, a lot of work has done some, heuristic-based or hand engineering rules to decide this communication. In this work, we sort of give this learnable module G, often as a as a neural network that sort of decides which base NAC structure or topology to use based on the current contact. So this learnable module will take as input the context, different content output that are corresponding base NAT topology or base NAT structure. So the input is the state or whatever however you represent it. The output will be a directed acyclic graph indicating the topology of this base NAT. Okay, and we want to train this for efficient communication. So in order to train this, it sort of can be quite straightforwardly plugged into standard deep multi-agent RL framework or multi-agent actor critic training. This is the framework we are using in this work. We have this G module take as the state as input and output the structure of the base net. And depending on the structure, agent will take observation, communicate, and then send their action back to the environment. The environment will, of course, make the transition, and those signals, including rewards, will go to a critic module that is responsible for computing the update of all the learnable modules here. So all the learnable modules, including the G, all the things that are in gray. So G, the critic, all the policies are all learnable modules.
One question for you. With this
Yeah.
model, does any one of them have priority over the others? Like it goes first and it decides, and the others follow based on it?
Yeah, so so for example, the G has to first output the topology before those agents knows whom to communicate with each other. So that in that sense, there is a sort of priority if you say there's a sequence of, so that cannot fully, parallelize with each other. But in training, so everything gets updated incrementally, so that how deep learning works. So everything gets incrementally updated. Eventually, we hope they will converge to some good solution. But once you deploy that, you want to basically follow this information flow chart. Yeah.
Curious, in the case of maybe like 3 separate agents, wouldn't this be feasible somehow to reduce it to a single agent, just like a central entity?
Yeah, we'll have some results saying that if you are doing all the dense communication always, then they reduce to a single agent thing when you want to provide some convergence guarantee or things like that. Yes.
Following up to that question, specifically for this application, doesn't it make more sense to actually learn just a single policy rather than learning in different policies for all the agents? Because especially for the screening task, number of agents are not going to be like way higher. It is easier to have a single policy, control them, so we do not enter into the issue of communication among them. And then it is even easy to optimize or learn, do everything.
Yeah, I think the idea is consistent to what you are saying, in the sense that doing training is effectively centralized or near centralized or near a single agent. But the final product we want to have is, by the end of training, when we deploy those agents, they want to, do the things in a decentralized manner. You want to remove the centralizer during deployment, after deployment. Does that make sense? So this is something we want. We want, during training, we want to leverage some level of communication to mimic a single agent mind, and during execution, we want still them to go on their own.
And would it be more effective if even during the execution, we have a centralized controller?
This will be, of course, more effective, but the thing is it feasible? For example, if you have 100 drones doing the thing together, you probably want them to do this in a decentralized manner, depending on how feasible the communication is with a centralized station.
So in this application, what goes into the state other than the positions of these robots?
The state is, for example, you can in a simulator, right? A state is a state in its rigorous sense. It's a Markov state, meaning that it has all the information it needs to decide on the next stage. So, but in for example, in a real world application, there's no such unless you are God, there's no such notion. So in this simulator, people often do is just concatenate or collect all the agent observations as a proxy of state or something like some notion of that. So this is when you do application-wise understand, you need to define some state that is near Markov. Thanks for the great question. So, and this is a core idea. We sort of tested this idea in different simulations, and I will highlight 2 of them. One of them is very toy example, which is called Aloha. The goal is that there are 2x5 agents, arranged in this 2x5 grid, right? So there are 10 agents. Each time step, each agent has to select whether to send or not send. Send means that it does not send any information to the neighbor, just send some message to, for example, to some base station or something like that. But if there are 2 neighboring agents sending the message simultaneously, they are causing a collision. So neither message is successful. Otherwise, they are successful. So in this example, because these 3 orange nodes are sort of neighbors with each other, none of message are sent. And these two green message are successfully sent. So every agent will have a backlog of messages that came as a stochastic process, and they decide whether to send a message or not at the current timestamp. Basically, they want to send as many messages. Okay, this is the first like toyish example. The other being a very popular simulator that cooperative RL and multi-agent RL people are often using to test their deep learning based solution, which is StarCraft 2 macro management. Basically, you are in a StarCraft 2 game setting. You are controlling a bunch of units that are grouping together as a team who is competing with another team consisting of several adversaries. Okay, so this is the two applications. In the first application, Aloha, when we test the learned basenet against, of course, the right no communication baseline and the right full communication, full dependence baseline, we can see that as the training goes, the learned basenet sort of, as expected, falls in the middle. And eventually it matches the performance of the full communication baseline. And that's not the whole picture. We have to say how many edges are there, right? So we plot the number of edges to measure for example, the communication cost, the dense level, the denseness of the basenet. We can see it sort of the number of edges goes from 50% roughly to 60%. It was initially 50% because it was a random neural network initialization. And the fact that it goes to 60%, not higher, 100% will be the full communication. Not higher means that we sort of can use less communication to sort of achieve the same level of performance in this Aloha.
This specifically this task that gap between no communication and full communication is very small. Yeah. Like, is it even effective to?
Yeah, I think it's depending on what do you mean by small, right? So it's of course not this gap is small compared to this part, but this days deep learning based are competing with small gapping state of ours. So this the fact that we run out is the fact that we can get significant difference is meaningful. It's understood to be a meaningful improvement.
And for this experiment, all the agents have their own action, but the state is global to all of them.
Yes, the state is global during training. Yes, but the observation is still you can see what the message how many messages you are getting, how many messages your neighbor is getting. I think that's the partial observability.
And during the execution, is it global or local?
What
The state always have to be global.
the state is global. If you concatenate those observations, I think the state is yeah.
It doesn't make sense to have different states, right? It's like the observation can be, the decision can be local observation. State
Can be local also to the agent. He doesn't need to know the whole state.
well, it never knows the whole state, only knows the observation, right? Because in order to first none of them know the whole state. They only operate through observations. But even if concatenating all the observations, it would you would have to concatenate it and centralize in the assembly others. But I don't have a good feeling of to get back to what was asked. I don't have a good feeling what does reward 5 mean? What does reward 6 mean?
Yeah, reward 5 means on average during the whole episode, how many messages are successful? I think this is the reward of this game.
Okay, let's
Thank you for the question, by the way.
On the second floor, what's BN?
Base net. A base net, number of edges in the base net.
Oh, okay. Is there any value in having a Bayesian network versus just topology, the actual topology based on proximity? Because people always define graphs.
Yeah, so in the simulator, there's no, specifically in this example, there's no proximity in any sense. You can send message however far away. There's no metric in those stages. But in the reality, there's always a range of communication for which there's an additional constraint you have to respect. But in a simulator setting that we cannot, I mean, you can sort of, engineer those artificial constraints there, but even if that's the case, still simulation, you don't convince that, deployment oriented people that.
But in some cases, did you find that learning a Bayesian network that has long edges?
Yeah, this is what I've shown. So when we check the learned base net structure, for example, in this case, the agent 7 always have 2, 3, 8 as its parents. So this is what being learned, not engineered. So in this example, 2, 3, 8 are as 7's parents, so which intuitively matches your intuition with because the game rule is you don't collide with your neighbor, so they will have to communicate extensively with each other. In this example, 137 gets their message successfully sent. In the same state, when we check the non-base net baseline, only 3, 6 will send their message with no communication, which means clearly there's one message less successful. But so you will occasionally find these examples that matches your.
Just a quick follow-up to this edges. So when it says 50% number of edges and then 60% number of edges, so it means what we are learning is actually to decide whether it is going to be an edge or not.
Yes.
It's actually the solving the task. So
What the G module, that G module is only responsible for deciding whether there is an edge or not. But that module has to be integrated in a bigger, architecture that ultimately decide what actions.
and then once we learn the number of edges, and with that we do the execution.
Yes.
So, okay, did you or somebody else investigate whether, so like in a base net, I can always draw a line, right? And that means nothing because the probabilities can work out in such a way that there is little or no dependence or something like that, and I just took a pencil and draw a line, right? This what something like that arrow from 3 to 7, what it really means is that the probabilities of in 3 affect the probability of 7. They are not.
Yeah.
Right, but that's a matter of degree. It might be.
Yeah, there is a matter, but the
So-
fact that they are removing other edges, but only keep these edges, is an interesting phenomenon.
It is, but how strong is the?
Right, so
like
it's-
that's the question.
Yeah, that's the question. I agree. So you can do more fine grained analysis saying that take all the neural net topology, base net topology and see whether there's a strong correlation between an edge existing and the actual probability distribution influenced by that edge. That is analyzable, I would say. But to answer your question, we didn't perform that analysis. Okay, so moving on to the second example, StarCraft, we see a very similar comparison between a qualitative comparison between the 3 curves, where our learner base net sort of outperforms the no communication baseline and matches the full communication. But when we check the number of edges, we can say it's saturated to 100% very quickly after training. So it basically degrades to the other extreme very, very quick. And we realized that it indeed could happen because there was no realistic mechanism that can prevent this from degrading to a centralized training. This is something we want to avoid eventually, because by the end of training, as I explained, we want them to be deployable in a decentralized manner. So as fewer communication is that.
What's the percentage of edges that you needed to keep in relation to the full?
Yeah, so that's a design choice you want to make. So, but we want to argue that there's no mechanism yet to sort of incorporate this design choice. So to incorporate this design choice, we sort of have a very easy and straightforward solution, just to incorporate another sparsity loss function that penalize the density of this graph to be not too far away with some eta that you predetermine. Okay, so during training, we sort of in the first part of training make this to be 100%. So if we don't really penalize any communication at the first part. The second part, we are annealing this eta all the way to 0%. We want to remove all edges by the end of training. So in this sense, we can clearly see that the number of edges sort of still saturated 100%. And then as expected, this sort of regularizer works and works it perfectly all the way to 0% by the end of training. But the price you have to pay is that the performance of the policy degrades. The interesting thing is that it sort of have such a V or U shape, such that by the end of the training, it's still significantly better than a no communication. The red and the blue are both use no communication by the end of the training, but the fact that you are doing some level of communication during training is helpful. Okay, so that's the more of the story we want at this. We do have some theoretical guarantee. If you have a full independence case, we have some results showing that there is efficient algorithm that can find you the Nash equilibrium policy. And if we, in this particular work paper, we sort of can generalize this claim to an arbitrary base net, but the caveat that how you have to fix that base net from the beginning to the end, and you can find a Nash equilibrium policy in the sense that it's consistent with this base net structure. So Nash equilibrium is sort of in some sense, the best thing you can hope for when you want to improve convergence, but it does not mean any level of cooperation. But if you are willing to reduce to the centralized full case, every Nash equilibrium will be an optimal policy, and you can sort of guarantee optimality at the right end. Okay, that's the guarantee we want to make. We sort of in a more formal statement of three is shown on this slide. The quick takeaway is that we proved it in arguably the simplest setting, where it's a tabular softmax base net policy parameterization. So basically, you want to parameterize your policy for every agent I with its state, its parent action because it was communicated to it, and its own action. So every tuple has a scalar responsible for that, and then you are deriving the policy in a softmax manner. So this is the parameterization that we are using to prove it here. So we won't spend too much time talking about its detail, but if you are interested, we can always do it afterwards. So, yeah.
From this analysis, was there any intuitive explanation which came out for any condition which says that, okay, if this condition is satisfied, I can expect to achieve the same level of accuracy with less communication? So that
yeah, this is the hard part. We didn't manage to do. So it's the hard part. Yes. Thank you for the questions. So I want to touch briefly on not briefly, but really go to the second part of it. So basically, when you are forming a team, in general, those agents are heterogeneous in a sense that they have different actuator sensors. And in a learning test setting, that means we have to parameterize their policies using different architectures and learn their parameters. But there are cases where those agents are homogeneous. And intuitively, these two robots are homogeneous. We didn't differentiate them in any ways. And rigorously, if you have a bunch of drones of the same model, they are homogeneous in some sense. even in a game like basketball, from the perspective of the referee, there's no difference between basketball player 1 and player 2 in a same team, right? So there are special cases, but they are very important special cases. So historically, in our community, to exploit this homogeneity, we sort of can use the same policy architecture to parameterize each agent. They still compute their update rule based on their own observation, but there is another centralizer that kicks in and to aggregate this update terms to perform a orchestrated update. And this is known as parameter sharing in our community. There's countless papers that have shown that this is particularly useful. But this work we are trying to answer, can we, rigorously justify this parameter sharing approach? I mean, to rigorously justify it, we have to sort of answer the first question of what do we mean by homogeneity? Okay, so I have to first come up with the rigorous definition of homogeneity, and then say in this homogeneous setting, parameter sharing is reachable. Okay. So to give a formal definition of homogeneity, let's consider this example again. Suppose they have their two respective action. One is going up, one's going to this direction. And after a time step, they are moving a little bit further, respectively. And the crucial observation is that if you swap the two agents, this M meaning a swap between blue and red, you swap their location and also their action, their velocity. And after a time step, they are still moving a little bit further in their respective direction. So the crucial observation is that if you swap them later, right, from the left, you swap the state on the left at t+1 state, you will get exactly the same state on the right t+1 state. That means the swapping can happen before or after the forward dynamics. It does not change the end result. So those agents are interchangeable in their dynamics. They can be swapped. So put it rigorously, if you want to rigorously define it, you want to have them having their independent local state, and you can do swapping between those states, and the performance measure is sort of equivalent with this operation.
In the previous example, can you go back to you were showing back on the examples for this, right? So the example you were showing, that's the Amazon packing robot, right?
Yeah, some warehouse.
Right. So you have the warehouse packing robot. So as long as there is nothing on that robot, they are interchangeable. But as soon as one of them carries some,
right? So you want to interchange their load as well. Does that make sense? So if I have a bigger robot, I put the same load on it. I have a smaller robot, I put this, there's nothing in it. When you swap them, you want to swap their location, their size, and their load.
do you have an action like that?
Action, the action means that how they are doing their motor maneuver. So the load means that load is part of state. You have to, incorporate that load in your state and do the swap. You cannot ignore this in your state.
Swapping means their ID plus their load. That's what it's swapping.
Yeah, so ID means their characteristics, meaning that so the load is part of state, something that you have to take into consideration as well. But I'm telling you that even with load is part of the state, it's just same as how those agents are making their choice in terms of their direction. So that has to be swapped.
So in your image there, you're saying each of those five agents and basketball players are homogeneous? Or?
Yes, they are. From the perspective of referee. When a referee deciding whether there's a violation of rules, they cannot differentiate whether you are player 1 or 2 or 3. They have to be treated as homogeneous. So that's the caveat. Not only their dynamics are swappable or interchangeable, so in order to give a reasonable definition, we also require their but I want to share this non-example to see if they are not homogeneous, how their dynamics are not swappable, okay? So we have two agents like this, but they are not homogeneous in the sense that the red agent is faster than the blue. They do the same action of going forward, but one is faster. And then after a time step, the blue robot is falling behind. If you swap the two agents like before, and then forward dynamics, the red agent is still faster. So it moves a little bit further. In this case, you cannot swap the bottom two state and get the same results right now. So that's sort of a subtlety, a non-example that verifies that our earlier definition indeed capture the homogeneity versus heterogeneity existing in this robot. Okay, so not only their dynamics are swappable, they have to be, swappable in their observation and rewards in order to make this definition useful, right? So which can be also rigorously formulated with this permutation invariance framework. Why this is useful? Because if you consider general policy, and if you swap the two agents, the red agent now has the same observation as the blue one, but they're using the different policies, then there's no guarantee about the subsequent route they will take respectively. There's no, because they are using different policies after swapping. The effect of doing this parameter sharing is just equivalent to saying that they're using the same policy given the observation. So after you swap those agents, not only their positions and velocity and directions are swapped, their future trajectory are swapped as well if you are doing this parameter sharing. So that's the effect of doing parameter sharing in this homogeneous agents. And we have theorem to justify this, it's optimized, saying that if you are swapping them and doing a search over constraint set of policies, then there is no loss of optimality in terms of the maximum value you can get, right? So this is the very first, but simple but very first justification of why parameter sharing is reasonable in this homogeneous agents. I think I have something on this work, but I would like to skip them in the interest of time, and briefly touch the third work. The third work is just here in this year SEML, where we sort of saying that we want to exploit geometric properties in those agents. And the idea is almost identical, the swapping thing. The only different thing is that instead of doing swapping, we're in a Euclidean space, which means that we can do Euclidean transformations of rotation and translation. So if you perform rotation and translation on those different entities and forward the dynamics, and you are a different state, then you just forward dynamics. But again, this two states at t+1 is sort of correlated by the same rotation and translation. So in the sense that those agents are equivalent to this Euclidean transformations, if you put them in a Euclidean space. You can sort of argue that this is also the case when you are reasoning about the policies, such that if you don't have any restriction on the policy, if the blue agent is making a turn and rotated by degree alpha, then from its own perspective, everything else is rotated by the same degree alpha, just counterclockwise. So these two observations are correlated by the same degree of alpha, but if you put what happened? So but you put the two observation as the input to a multi-layer perception-based policy, there is no guarantee that that action will be, rotated. So if you are restricting the action is also going to be rotated by the same alpha, then we call it a symmetric policy in the Euclidean sense. In that, so we cannot, hope that multi-layer perception can do the work. But the same theorem happens. So if you are restricting this policy to be symmetric, then there's no loss of optimality if you can afford to search for the best policy within them. I think what's interesting that even if for our arbitrary layer perception-based policy, you cannot sort of guarantee symmetric output, this symmetric output sort of naturally emerged when we were training such a multi-layer based policy. I mean, initially with zero initialization, you have roughly this level of symmetric output. And as the training goes, the level of symmetric input and output by rotation and translation sort of grows. So it's sort of the neural network is learning such symmetric properties embedded in this game over time. Okay, so the natural question, idea is to just fully replace this multi-layer based perceptron with a special architecture of equivariant neural network that can guarantee this symmetric input and output, no matter what the parameter of the neural network is. The very specialized neural network can do so. And you can plug in this module to replace the regular modules in your neural net architecture in a multi-layer, replace those multi-layer based modules in a regular neural network architecture and achieve the symmetric results automatically. Okay, and we have sort of tested this work to perform really well over different. This is the kind of this particle movement example, but we have shown that it's outperformed the baseline by a really large margin, and we moved to the locomotion example where there are multiple limbs joined together with this together to form a robot that can sort of you want to move the robot in a certain direction, which is called locomotion in robotics. But the lesson is that as we are increasing the level of the amount of symmetries in these games, however you measure one, because this card pole has very limited number of symmetries, but this reacher has a very rich number of symmetries. So we can see that our methods labeled by this red curve is sort of reflecting the number of symmetries there, because you have a large number of symmetry that has a very large value, right? So if you have a very limited number of symmetry, it has a very limited value. Okay. It's 10:50. I want to spend the last 10 minutes talking about the future, and I want to take any questions. So I've talked about 3 representative work and some ongoing projects that I have. So for structured communication, we've talked about action communication, which happens at every time step in general, okay? But in reality, it's often the case that you can only communicate with a peer at very limited number of time steps during an episode. So in that sense, what we found is that you don't want to just communicate the current action, but you somehow want to communicate the intent that's going to be relevant several time steps in the future in order to make your communication more effective. So this is kind of the work I've been focusing on in my PhD study. I will continue doing such work with the support from NSF. Okay, so this is the first category of my future work. The second being the homogeneity versus inhomogeneity and geometric properties. And I'm sort of grouping them as 2 important subclasses of multi-agent symmetries. And this work has been sort of supported by my career grant. We sort of have 3 different research tasks progressively. One is to identify and exploit the exact multi-agent symmetry like rotation and swapping that I just talked about in this talk. And moving on, we want to deal with the approximate symmetry. For example, if those 2 robots are not identical to each other, they are differ in their size, but only slightly, right? And totally they don't satisfy exact symmetries, but their symmetries are approximately symmetric. So we should still be able to exploit this by a little degree, by a huge degree. And third being that we have been showing the benefits of exploiting symmetries empirically can we provide some theoretical guarantees when you are exploiting the symmetries in your policy, for example, policy optimization, things like that. And looking even further, my current research has mostly focused on theories, architectures, and algorithms. So, but it's just the one piece of the puzzle that if we want to realize the dream we had in the beginning, we have sort of a bunch of autonomous agents working together in reality. So the other missing pieces, including perhaps we want better benchmarks and simulators of high fidelity, it matches the expectations of the real world practitioners. Historically, these benchmark and simulators have been driving this research field for a long time. So this is why it's really important. Second being, can we sort of move the success from those simulators to some engineering application or science applications? And third being human teammates. Can we incorporate human teammates? Because eventually those agents are benefiting humans. If we want them to be more useful in a human involved setting, then human teammates have to be incorporated somehow. So I want to sort of emphasize maybe this human teammates puzzle, right, piece. So historically, we have been studying non-human agents because they are easy to do during simulators. It's very sort of cumbersome to sort of hire human and that human as a teammate of your agents. But right now, because we have sort of this large language model, at least they are capable of mimicking human in a language sense. Okay, so if they are having a good amount of language capability, they can reason and communicate with language. So if we plug those foundation models as part of the team, so what will happen? Okay, at the very initial step, I'm collaborating with a different PI from UC Riverside. This is the RI proposal I was very excited, was just recommended last month, where we have the 3 struts that sort of take the first step to incorporate this foundation model into the team. And we have 3 struts, 1 and 2 for single agent setting, and 3 for multi-agent communication. I will go into highlight the first one, right? So we consider the contextual bandit setting. And we are saying that if you're using a standard bandit algorithm, then it's going to be asymptotically optimal, but we'll have to learn from scratch at the beginning. It's slow if you are plotting for example, the regret curve. But if you're using these large language models, it's probably a little bit difficult to improve these models over time because they are large. It's not that easy to fine tune them to make the same performance guarantee. But what if we combine the best of both worlds? So we are having initial results showing that we are doing BERT as a large language model and the bandit algorithm, and then we are doing a mixing over the 2 base learners, saying that during the learning, let me query the language model for some time step and switch to the bandit for another time step, and what will happen? So intuitively, it should combine the best of both worlds. And our results successfully sort of justify this hypothesis by saying that we are plotting the BERT performance as a straight line, as a horizontal line, because we are not updating it. And the standard bandit will sort of pick up from scratch to match the performance of the language model after this many time steps. But if you are doing a crawling of them, we are doing much better than both of them. Okay, so I think I want to stop now because I have a few more slides to show the future work. But I want to stop now and to take further questions from you if any. Thank you.
Very much.
Yeah.
About scalability of learning by agent networks.
Yeah.
Talk about agents. How many agents can you learn?
Right. So in that scenario, if you're doing StarCraft, we can afford learning up to 10 agents in that game. But if you kind of, so it's the scalability basically comes from two sides. One is, can your simulator afford this amount of agent? And two is, can your algorithm afford them? I think basically right now we have more and more simulators that are scalable, which can sort of simulate a large number of agents simultaneously. But that algorithm, it has a caveat that because it's taking the state and the compute of whole the whole basing net, so it's fundamentally constrained by how effectiveness can you sort of sort this out algorithmically. So we, in the example, we can scale it up to 10H, but I'm pretty confident if you have a good simulator, 10 or 20, 30 agents, you probably cannot figure out the best base net very effectively, but it's certainly better than a than a random based net or than a no communication baseline. Yeah.
So I have a question about the swapping that you did in both the last
Yeah.
2 parts. So is that related to the concept of exchangeability, probabilistic models in which people, instead of independence, they found that there's between random variables, they find that you can essentially get very similar results under a much weaker requirement, which is the exchangeability, that the distribution remains invariant to permutation.
Yeah, I think that the underlying, thing is that can you found structures in your transition kernels, and the specific structure that we are identifying here is exchangeability. Maybe that's relating to the probability literature that you were referring to, but I'm not very familiar to that. I would say definitely yes. There are some work that studies the structure of the probability kernel and argue about how the structure is popular enough to earn your attention, and how useful you can exploit those structures to design better solutions. Yes, definitely.
Well, the question that was asked on scalability, is it easy or possible if you don't use the Bayesian network approach, or instead just look at some of the metric used?
Yeah, I think that would be possible, but the uniqueness of this work, why it is sort of published and get some positive review, is that it's an initial step that sort of drive the community away from that fully decentralized and product policy. There are a lot of follow-up work that sort of adopt a similar idea to say, let's increase the communication during training and suddenly try to remove them by the end of training. But I think that's one of the first work that tried to drive the community away from just a product policy in this deep learning based solutions. Yes.
Question about one of the future work that you mentioned. It was regarding the fact that action communication is not too real to given.
Yeah, right.
So you mentioned something about including the intent for future. So
yeah,
is it something where you are planning to maybe test out some random communication outage, and then we can see how far that intention can be used by other agents when it comes to
random communication outage. So yeah, the communication outage is, if you are doing research, you probably want to start with random communication outage, because you can get quick results. But the communication outage sometimes can be even planned. For example, let's stay in this room at the beginning, and let's return to this room in 5 minutes. So that 5 minutes, outage is planned. So yes, I mean, in the optimality sense, you want to make that outage as another decision variable to optimize. Yes. Thank you for the question. I mean, it's great. Yeah, thank you so much. Yeah.
Are there any questions from Zoom?
Yeah.
I will.
We're gonna be going upstairs
Sure.
and then close this out.
Okay.